Swayam Prabha. Digital India. Educated India.
Welcome to 18th lecture of video course on Tribology. This is our last lecture of module 4. We have covered 3 modules earlier, that was introduction of Tribology, then friction, third module was on wear, and fourth module on lubrication. And this is the last lecture in lubrication module. The topic of present lecture is lubricant additives. It was mentioned earlier, it is very difficult to get the best performance by single lubricant without any addition to that or simple base oil. We require number of properties, and on a single oil can sustain or provide those kind of properties. That is why we require lubricant additives. In last lecture, last to last lecture, we covered EP additives and friction modifiers. Those were additives mixed with a mineral oil to enhance the property related to friction and load carrying capacity. Today, we are going to cover few more, but before we start up that, there is a need to spare some time finding what is the need of these additives with some examples. First example is the gears. Say the gears are subjected to very high contact stresses, and due to the high contact stresses, lubricant will be squeezed out. There will be metal to metal contact. To avoid the failure, to avoid the seizure of gear, we require EP additives, what we call as extreme pressure additives. As in earlier lecture it was mentioned, is a misnomer. Even though the name says extreme pressure additives, they work with the temperature. They are effective at the high temperature, and because of the high temperature, seizure occurs, welding up to component occurs, and we want to avoid that. That means, EP additives are effective at the high temperature additives or the high temperature. As I mentioned, the typical example is a gear. This is a simple solid model of the gear pair, and there is a contact shown over here. The whole gear load is transmitted on either on one tooth pair or 2 teeth pair or 3, depends on the contact ratio. Let us take an example of the one tooth pair. So, one tooth of one gear and one tooth of pinion are in contact. If I magnify this, I can see the contact over here. This is very small patch. The whole power is transmitted at the dispatch. Naturally, contact stresses would be phenomenal. An interesting thing is that all other gear teeth, they remain ineffective that time. It is only the 1 or 2, depends on the sliding ratio or contact ratio. Now, if I further magnify stress pattern at this patch, I am able to see this stress pattern. The right portion shows a stress equal to the 2 gigapascal. 2 gigapascal is very high stress. Ordinary steel strength under compression may be around 500 megapascal, 600 megapascal without heat treatment. That means, these kind of gears require good heat treatment to improve their compressive strength. And that is why I say that improving its strength is a one point, but at high contact, very high pressure, wear will be phenomenal if we do not use EP additives. Wear in terms of seizure, we say that complete binding of gear pair, they will not be able to separate. To avoid that kind of thing, we require EP additives. Let us take another example, say IC engine, typical tribo pairs which sustain, which bears all kind of conditions, and major thing is a high temperature. We know operating temperature of most of the components are more than 100 degrees centigrade. Even the cooling water is used, but operating temperature will be 100 degree plus, because we do not want to lose efficiency. In that case, all the liquid lubricant need to be resistant to the oxidation, otherwise oxidation will happen, and due to oxidation there will be some sort of deposits on the metal surface that will further hinder the functionality of those components. That is why we use detergents and dispersants to avoid hard deposit to be fixed or made on the surface. Similarly, because of the high temperature, there is a more possibility of acid formation from the liquid, which will corrode this component. That means, we need to use corrosion inhibitors also. And as in the previous lecture, we discussed about the multi-grade oil. So, engine works with a different temperature. At the start, temperature may be 20 degree, maybe 30 degree, maybe 40 degree, maybe 50 degree, depending on the environment, and it reaches to the temperature more than 100 degrees centigrade. So, it requires variation in performance based on operating temperature, and that is possible by multi-grade oil. That is why we require additives, and in previous lecture we mentioned that we use a polymers, we add polymers, those are polymer additives, will be known in a class of the additives. The third example is a refrigeration system. We know the refrigeration system need to operate at a very low temperature, that is the meaning of the refrigeration, and lubricating oil require a flowability to get circulated from one place to other place, so that it can carry wear debris particle. For that purpose, we require low temperature lubricant. As I mentioned that we require number of properties from a lubricant. In this situation, we need to add additives to impart low temperature properties as well. So, this is indicating there is a really a good need of additives, and in commercial oil available in the market, we do not find any oil without any additives. There will be some additive one form or other form. For engine case, this slide shows some sort of experimental results. Say that when the engine bearings, assuming the stainless steel, assuming the chromium steel surface 1 and chromium steel surface 2, we do not use any lubricant. Then we find the wear constant, or the probability of formation of wear particle is roughly 10⁻⁻3. Using paraffinic oil, which is a good oil, good lubricating oil, this probability decreases, it reaches somewhere 10⁻⁻7. That means there is a benefit of 10,000 times, wear will decrease roughly 10,000 divided by 3, the 3,000 times. Now, if we use a paraffinic oil with temperature additives, temperature resistant additives, corrosion inhibitors, then wear rate will further come down. That shows a 10 times benefit compared to simple paraffinic oil. Now, we use a complete package where the anti-wear additives, EB additives, all additives, anti-foaming additives, everything is mixed. That is what we know as engine oil. that is a complete package. That wear rate decreases significantly, even the benefit compared to that observation is around almost 100 times. That means, if you want very low wear rate, we should use additives, but without understanding we cannot go ahead. Additives, they conflict with each other. There is always an interference of one additives with other additives. You think over, we use a soapy layer to avoid the deposits, but the soapy layer itself may corrode the surface. So, there is always some sort of contradiction, and to avoid that kind of contradiction, we need to understand what are those additives and how they function. In brief about the additives, we can say we require a number of properties from the lubricant. That is why we require additives. We require adequate firmness strength from a lubricant. Example was given about the gear pair, where the contact pressure is more than 2 gigapascal. That means, a firmness strength need to be that much level. Further, they require chemical stability. Liquid lubricants are many times in acidic nature, and they will corrode the surface. So, in that case, we require chemical stability of those lubricants, as well as a non-corrosive nature of those lubricants. To give a firm strength, adequate strength can be termed in a EP additives time or in boundary additives way. Further, you need to be free from a contamination. It should not happen that liquid lubricant is coming with some sort of contamination from environment and creating more and more wear or developing more wear. In addition, if there is a possibility, they have some sort of sealing properties, which is very difficult to think, but it is required. Otherwise, you will be requiring additional seals, additional components. They need to have a high VI. They should not change viscosity with the temperatures to significant level. We know it is inherent in liquid lubricant to decrease viscosity with increase in the temperature, but the rate of decrease should be controlled, rate of decrease should be low. And finally, comes outgassing. It should not happen that liquid lubricant turn out to be vapor and evaporate. Sometimes we are keeping 1 liter of oil, and after some time we find, oh, it is only the half of the oil is remaining and half oil is evaporated, which is not desirable, and we should use additives to avoid that. Sometimes we use metal as a liquid lubricant additives also, or they form some sort of chemicals with acids, esters, or some other basics. So, what we say that liquid lubricant can be defined as elements which incorporated either in a liquid base or grease. So, we are not avoiding the grease, we are saying that liquid and this lubricant additives also come in grease. And liquid lubricant, not only the mineral oil, it can be added in synthetic oils also. But what is the requirement? They need to be soluble, properly mixed. It should not happen that they are floating, and uniformly dispersed. If it is not uniform distribution, then few metal parts will get a good lubricant and few metal part will not. So, we require a uniform distribution. There are some metals, metal elements, or we say that some material elements which have been used as additive are listed on the left and right hand side of this table, and their function, their action is mentioned on the left hand side. I used a word earlier, the detergent or dispersant additives. We know the soaps are generally made with the elements. The calcium is one of the common elements, sodium is a common element which is used to make the soap. Similar elements can be used to make a detergent and dispersant. How detergent and dispersant acts, we will be covering in a few slides in the next few slides. Similarly, we have discussed extreme pressure additives. We talk about the chloride, sulfur and phosphate, but they require some sort of element to react so that the layer can be made. One of the common EP additive is a boron. Coming to the antiwear, we have number of options available. So, lead, zinc is one of the very common antiwear additives, copper, phosphorus. Now, there is a slight change. We say that EP additives and antiwear additives, they work by and large similar manner. EP additives also provide a strength to the surface, reduce the wear by reducing the seizure capabilities or capacity of the metal pair. Antiwear also is the same thing, it avoids the wear, it coats a thin layer on the surface. So, functionality point of view, both have a same function, but operating temperature is different. In EP additives, the operating temperature at the junction, at the interface is higher than the antiwear additives. That is why initially the antiwear came, and after that when we provided our additive provided extra strength, that were treated on those additives were named as extreme pressure additives. In last lecture also we covered friction modifiers. You say all sort of solid lubricant act as a friction modifier. They require some sort of carrier fluid, so that these particles, the particles of solid lubricant can be transferred from one place to the desirable place. So, this is the friction modifier, and here example is given the molybdenum disulfide. It can be silver also, it can be graphite, it can be PTFE. We have huge number of additives in this category. Then there are two interesting additives, what we call anti-foaming additives. We use a dispersant and detergent for their functionality, but these additives create anti-foaming problem. They make bubbles, and we know very well the bubbles, if there is bubble, then flow rate will come down. That will hinder the flow rate or reduce the cooling capabilities of that liquid. So, we require anti-foaming additives, and element is used in the silicone. Similarly, we have antioxidant additives, which reduce the chemical reactivity with oxygen and increase the life or service life of the lubricant. Zinc is one of the most commonly used. That is why we say that zinc based additives can be used as the anti-wear additives and can be used as the antioxidant additives. It can work as dual purpose, it can fulfill dual purpose. Let us start from a first category, what we say the detergent or dispersant additive. There are different theories, different hypotheses how detergent works. What we feel that detergent forms a protective layer on the metal surface to prevent deposition of the sludge unvarnished, which comes from burning of lubricant and after getting oxidation. So, those should be avoided. That is one function, but there is another possibility that additives who can this kind of additives can wrap around particles and avoid the increase in the size or growth of those particles. Often presence of detergent is measured with the TBN number, what we call the total base number. We have a 2 number, we quantify detergent or add these additives with the 2 numbers, the TBN and 10. If the acid number is increasing, that means the base number is decreasing. And that is why we say that we should check these numbers if we want to find out whether there is sufficient detergent or not, if there was an intended function of detergent. And these are the some elements name given which help in detergent. Now, what we are discussing with what is the functionality of detergent. I am assuming that there are some wear debris, there are some sort of sludge particles, some sort of non-desirable particles coming near the surface. So, I am assuming this line is representing any metal surface. I am keeping in a vertical direction, and these are the particles maybe in a nanometer size or maybe in micron size. They try to come and get deposit on the surface. They have some sort of gumming characteristics, they have some sort of adhesiveness, they will come and stick to the surface, but they do not have a good properties. They may be having a wear properties also, they can scratch on the surface. So, what is required? We require to avoid this kind of accumulation of these particles. If we are able to avoid this kind of accumulation, this kind of additives can be removed easily by filtration system, or even if they are not removed, they remain in suspension, they are not going to harm the surface. Service life of that tribopair will be much larger. So, this is the main function. Do not allow accumulation on the surface, and let the surface be free from these particles as far as possible. And this is possible with some sort of soapy characteristics. So, that detergents or detergent additives, they are soaps of high molecular weight, which can stick more easily to the surface. If the low molecular weight it can be removed easily, high molecular weight they stick too much, or we say with a greater force, and they need to be soluble in oil. It should not happen that they get separated from the oil. This slide shows some sort of a hypothesis, not 100% correct, but some sort of hypothesis how detergent will act. We say that detergent acts because of the binding agent, particles they get accumulated, agglomerate on the surface because of the binding agent. Now, have two approaches, either encapsulate this particle or encapsulate binding agent, so that they do not stick to the surface. I can simply take analogy from police and crime action. So, criminals are generally kept in cell away from the society, they should not harm the society. It is nothing, there is no purpose that you take those criminals and kill them or beat them in prison. What we are doing in this case is the same thing, we are trying to keep a cage around this particle, they do not agglomerate, they do not spoil the metal surface, we are trying to keep it away from the desirable surface. The same thing, we are assuming there is a detergent, and then detergent tries to encapsulate binding agent and let particle be free. If particle is free, it cannot have, it will not have a binding agent, it will not increase in its size. That is the one point. There is other option, encapsulate this particle and let binding agent be free. So, either of this approach will work, it will solve the purpose for which we require detergents, and this analogy works with almost for every additives. We have a number of examples, we will explore those. Same action with dispersants, only the difference comes that is indicated here. So, that detergents like dispersants are blended in lubricant, they are mixed with a lubricant to remove and neutralize harmful product. Remove from surface and neutralize. But in addition, detergent has additional say functionality to form a protective layer on the surface, while dispersants they do not have that functionality, they do not require that functionality to make a protective layer on the surface. So, in this situation a dispersant with anti-wear additives can be utilized easily, because they do not make any layer, but they try to suspend particles. It may be a dirt particle, may be a undesirable water, undesirable fuel, or some sort of processed fluid, or oxidized product or burnt product, that too within liquid lubricant. So, we can say dispersant isolate the particles from each other, they make a barrier between the particles and they do not allow particles to join together. The way we have understood the boundary additives, they have also similar kind of characteristics. They have a polar head and the long tail. Long tail is required to get suspended in liquid, and polar head is required to get attached to that particle. Now, depends on which particle we want to encapsulate, which particle we want to really capture, additives will change accordingly, but they will be in the same category of dispersants. That is we can say they have almost same functionality as a detergent has, but detergent will have additional property, additional requirement compared to dispersants. We have anti-wear additive. Say that anti-wear additives may work like a boundary film between the metal pair. It prevents metal to metal contact by making a thin layer, thin coating on the surface. So, it has both the function to reduce friction and as well as a reduce of wear. Reduce friction because they make interface weaker, and allow lesser friction or lesser torque to be exerted on the surface. But to differentiate from the EP additives, we are mentioning this kind of surface is for lighter to moderate load. If there is a load is extreme load, very high contact pressure, then we are bound to use extreme pressure additives, which have more bond energy compared to anti-wear additives. And couple of examples are given. We have already discussed about the stearic acid, which is a boundary additives, is a polar lubricant additive. It has a polar head to get attached to the surface, and until the way we mentioned about the dispersant, they have almost a similar kind of physical form. Zinc compounds, ZDDP is one of the common component used, common additives used as an anti-wear additive. Even the molybdenum disulfide and the graphite can work as an anti-wear additive, because they really reduce interface shear strength, they reduce the friction. So, they can be named, they can be put in a category of anti-wear additives. Next category is the anti-foaming additive. This picture shows the foaming action of a liquid lubricant. It often happens in the bearings when we are pressurizing the liquid to pass through the convergent region, inclined surface. As the liquid is pressurized and passed, when it release, it comes with some sort of bubbles because of surface tension, and they remain in a bubble form. So, easiest way is that reduce the surface tension, collapse this bubble as soon as possible, because if there are so many bubbles, the pumpability will reduce. We require extra force to pump the liquid. In addition, these bubbles may keep some sort of air or oxygen with that in contact with the surface. So, they will increase corrosion probabilities or rusting probabilities with that, and we want to avoid it. We say that anti-foaming the foaming can be defined as a formation of air bubble in the liquid. When we are talking about the air coming into contact with the liquid or coming in a contact with the solid surface. Sometime due to shaking and all this kind of foam will be made, and if we are using detergent and dispersant additives, foaming will be slightly on the higher side. That will increase the tendency of foam or making bubbles in liquid. As I mentioned, it interferes with flow rate. In addition, they interfered with the heat transfer also, because the air has a low heat transfer rate, liquid has a high heat transfer rate. But if you are providing some sort of bubbles in between, or some sort of bubbles are coming in between, overall heat transfer rate will reduce because of this. In addition, this foaming is undesirable from oxidation point of view, as it provides air or oxygen to surface. Now, we need additives which reduce the surface tension between air and liquid to collapse the bubble, and one of the common additives is based on silicon. The silicon polymers are used in very small quantity in liquid lubricants to avoid the foaming, to avoid the effect on heat transfer and mass flow rate, to reduce the possibility of oxidation as a collapse of the bubble before reaching to the contacting surface will reduce the oxygen or air which is carried over the surface. Now, as I mentioned about the cage around the undesirable surface, undesirable particles, same thing we can explain action of antioxidant additives, or sometimes we use the word oxidation inhibitors. They encapsulate oxidant itself. Say that oxidation happens at the high temperature and high pressure, and if the oxidation happens, what is the loss? Some sort of gummy deposits will be made on the surface, reduce the clearance, change the physics, change the mechanism, and cause undesirable functions or undesirable failures of those tribopairs. And when this kind of gummy substance happen, they are very sensitive towards a couple of materials like a copper and lead alloy, which are very common bearing materials. That means, if we are using a oil for the engine, we need to use antioxidant, otherwise all the bearings will get corroded. Similarly, as I mentioned, that it reduce the clearance. In addition, what we say, because of this gummy substance, the viscosity of the liquid will increase. If viscosity of the liquid will increase, that will cause more and more friction loss, more power loss. How they function? We are trying to keep the same minute. We have some sort of additives in oil. Whenever they find oxygen nearby, their chemical affinity is more than the liquid lubricant. They immediately come around oxygen, react with the surface and consume that available oxygen. But as these are chemically acting with the oxygen, the depletion is obvious. After certain duration, antioxidant need to be added again in oil, that is why we call as a reconditioning of oil. You need to change the lubricating oil by adding some sort of additives in liquid lubricant, either directly we cannot do directly. So, that is why we require some sort of a refining process. And often that is quantified when this oil need to be replaced by 10 number. This is one of very common parameter. Whenever we check the lubricant oil, we will be discussing this in oil conditioner monitoring. When we want to find the health of oil, we go ahead with the oil conditioner monitoring. We try to find out the parameters, whether element have depleted or desirable properties have depleted, and that one check is a 10 number. The 10 number more than 3, that means it does not have antioxidant additives, it is ready to oxidize, it is going to increase the viscosity of oil. The better you replace it with a new oil, or you need to recondition that oil. There are some other additives what we keep in the same category, that is known as the corrosion inhibitors and rust inhibitors. We are keeping in the same category, being a reason that rust is a name given with a ferrous metal. If ferrous metal gets corroded, that will say that is rusting. This is only the English language change, chemical form will not be different. When corrosion, it is corroding the surface, is making some sort of porous layer on the surface, and that is easily removed, that can be easily removed, that will cause a wear rate on the surface. Keep in mind, we use anti-wear additives also as a corrosive agent, or we say make a corrosive layer on the surface, but the thickness of that corrosive layer is much smaller. While here we are talking about the corrosion rate is much in that earlier case the corrosive layer was smaller, while in this case corrosive layer thickness is more. Thin layer has almost same strength, but a thick layer of corrosion will have a more strength, lesser strength, and can be removed easily. Now, we say that this can be avoided by removing oxygen, which is dissolved in a water or oil wherever metal surfaces are used, and again getting consumed. So, we need to replenish it. The depletion is possible, we need to recondition. Again, how they are working, you can see there is two different forms which are shown. It has a polar end and this long tail. You see that it comes in a surface, attack on the surface, not attack, it attached on the surface, and does not allow oxygen or water molecule to come near the surface, keep separation from oxygen and water molecule. That is one way. Physical point, and chemically they make some other form which is not harmful. Now, again we can say mechanism, one hypothesis is that this kind of additives, they are making thin layer and providing shield against oxygen and water. That means, every solid lubricant should work as a rust inhibitors. It comes in a contact and attached to the surface, reduce the chances of rusting, reduce the chances of corrosion. If we are using anti-wear additives, that also are rust inhibitors, that is a contradiction. We are saying anti-wear additives as a chemical form, they make corrosive layer on surface to prevent further corrosion. So, they can be used, we can use a word for rust in anti-wear additives as a rust inhibitors. They allow corrosion for small scale only, for finer level only, which is negligible. And there are some example given in the phosphate we have already covered. It makes a layer on the surface, low friction surface, and avoid the further rusting of the surface. a kind of additives or a pour point depressant. We say that a refrigeration system we require a operating temperature much lower than 0 degree centigrade, where the most of the liquid lubricant will not be able to flow easily unless they are mixed with some sort of additives. So, we can say for lowest temperature at which lubricant will flow, in absence of additives, they form some sort of crystals. These are waxy crystals. They increase the viscosity drastically. As there is a drastic increase in viscosity because of the waxy characteristics, they will not flow easily and will not reach to the desirable place. So, if you want to avoid that kind of crystal formation, we should not allow one crystal to come in a contact with other crystal. It is something like a divide and rule. You divide all the crystal particle, you remove one from other, and do not allow agglomeration of those wax particles or wax crystals, right. So, what we say that we try to avoid the wax formation, or you change some sort of a structure of this lubricant, so that they do not thicken too much with a decrease in viscosity, decrease in temperature. We say that this kind of pour point depressants, they reduce a pour point and can work with a low temperature. Methyl acrylate polymers are one of the common pour point depressants. We have covered few additives, but as I mentioned that gaining the knowledge will always be helpful, as we have understood that solid lubricant may act as a rust inhibitor or corrosion inhibitors. That means, when we are doing a coating of solid lubricant on the surfaces, then we do not really require additional rust inhibitors. If we know that kind of solid lubricant will remain there for a long service life. But if there are some detergent and rust inhibitors, then we need to be very careful about physical attachment or chemical attachment of additive to the surface, because detergent and rust inhibitors, they will try to separate antiwear additives from the surface. That means, we require a perfect combination, a perfect percentage of detergent and rust inhibitors with antiwear additives or ZDDP. If I am keeping 3% of ZDDP, which is high concentration, we know higher the concentration, more possibility of attachment to the surface, and a low percentage of the detergent, but that low percentage should not be very low, which avoids this functionality. So, a good permutation combination is required, good number of experiments is required, as a really very hard research area. People have done a lot of research, but they are keeping all in a closed book, they do not share easily, and that is why the most of the industry, they do not document or they do not publish results. They publish the results only metal A or element A is doing this, or a complete package is working satisfactorily, but they do not share all the results. Now, there are some precautions which we need to be accounted. We say that corrosion inhibitors, if used within the ammonia plant where there is a possibility of ammonia leakage, then there is a possibility of damage. So, try to avoid corrosion inhibitors in presence of ammonia, which has a possibility to damage the overall system. Then we are saying whenever there are dispersants available or used, we should use antioxidant along with that, because we know dispersant will allow more and more oxygen or more and more air to bring near the surface. They will collapse the bubble, or they will make in such a manner encapsulate the surface remove the coating from surface, allow free surface to be getting exposed to oxygen. So, we should use anti-oxidation for that purpose. Now, there is a this is the last lecture. So, I am giving a few slides on the lubricant selection. This slide is taken from one of the handbook, which shows some limits for the grease, solid lubricant and liquid lubricants, but these are not very strict limits. That is why you can see the band from one lubricant to other lubricant, there is some sort of a variation is possible. So, we say that the low speed, in this case the speed on x axis is given in mm per second, while pressure on the y axis is given in kilonewton per meter square or kilopascal. Now, for the solid lubricants, for dry lubricants which do not flow, speed and the pressure limits are lower. You can see this kind of rectangle, that is a lower, and this is the transition. Some sort of dry lubricant also can act in this way. This is the minimum limit, as this is variation. Now, there is a limit for the grease when the grease is being used for plain bearing or employed for the plain bearing, but the limit for the rolling element bearing or the grease limit for the rolling element bearing is on higher side. That is interesting to note. If I use a similar grease, there is a lower limit for the plain bearings, but higher limit for the rolling element bearings. What is the reason? Say that in a plain bearing there is a more sliding, more friction, more heat generation for the same heat speed because of the high coefficient of friction, while in rolling bearing coefficient of friction will be lesser. So, more speed can be allowed for this purpose. Coming to the liquid lubrication, it has a higher speed limit, but lower limit compared to solid lubricant, particularly for the pressure side. Highest limit is for the solid lubricant, which can sustain more pressure. As I mentioned, these data are taken from a handbook. Handbook is around 30-year-old. So, this gives a guidance, but not a firm limit. We can see, if there is a limit for the dry lubricant, I can try grease. If there is a limit for the grease, I can try for the liquid lubricant. If there is a limit for the liquid lubricant, we can try gases. If the speed of operation is increasing, while if the pressure is increasing, we will shift from a liquid lubricant to grease to dry to the solid lubricants. Some important points have been given on this slide. So, that start from scratch, choose lubricant which only meet the friction and wear requirement. That is the first point for tribological applications. However, if the design says that now these liquid lubricants are also required for cooling, then lubricant selection will change, and there is too many contamination we require to carry this liquid lubricant. This kind of contamination do not allow to get accumulated at one surface, the liquid then choice will be different. Or if there is a possibility to avoid the corrosion, take an example of number of metal parts, steel parts, when they are finished, when they are fabricated. Let us take an example of lathe machine. When we fabricate a shaft on the lathe machine, give a finish to the surface, immediately you can see the labor or person who is involved in fabrication, he will apply a grease layer, so that a corrosion can be avoided. So, we say that if lubricant is required to avoid a corrosion, the choice will be different. Liquid is required for cooling, choice will be different. Liquid is required for contamination, to avoid the contamination, the choice will be different, but we are concentrating more on a friction and wear requirement. These are the prime requirement. there is a possibility of additional requirement, there is a possibility of temperature is going high and we need to keep lower temperature, then the cooling can be added aspect. That may be quite possible. We can use the same lubricant, but with a pressurized liquid to allow more and more cooling. So, keep in mind, we are thinking only from friction and wear point of view, and then we are suggesting how to select lubricant. So, first step, think about the cost. It should be lowest cost for commercial application. Lowest cost need to be there, or otherwise we will not be able to justify our selection. And if possible, think about the no lubrication or no re-lubrication system. Once we applied, and then think we do not have to re-lubricate it again and again, and we are away from this kind of worry. Typical examples for that this kind of application is the watches. We know that the lubricant cost is very high, then we will not be able to use in watches, clocks, door locks, the cheap components. Swing machine, we do not require re-lubrication frequently. Swing machine, other than swing machine and all, door lock we do not do unless some sort of corrosion happen because of the environment. So, think about the cost, think about the re-lubrication. If try to avoid the re-lubrication, try to keep minimum cost. That is the first step. After selecting that, if selected lubricant is not fulfilling the function from point of view of this second step, you say, is there any need to change the lubrication system? Suppose I selected some sort of molybdenum disulfide, which is cheaper, or I selected a graphite, which is cheaper, or PTFE, which is cheaper. Now, I had to check, am I really getting the right results, desirable results? That is why I say that, is there any need to change the lubrication system due to excessive load? If there is excessive load, if I assume the PTFE and I say there is a load is very high compared to PTFE requirement, then I will choose a better lubricant, which is the molybdenum disulfide compared to this, or if I will choose a graphite and then choose a molybdenum disulfide. Or if the speed is higher, then may be quite possible we need to think about the semi-solid lubricant from the solid lubricant. The speed of operation is more than what is satisfying a solid lubricant, or heat of generation is very high, then need to be cooled. So, naturally we need to go for the liquid lubricant, or there are too many debris and we require a carrier fluid to carry the debris, then we require liquid lubricant. So, we say the first we choosing the solid lubricant as such, because the lowest cost, no re-lubrication requirement, but because of the once we select and we try to justify whether it is really satisfying all the requirement, is satisfying the speed requirement, is satisfying excessive load requirement, is satisfying heat requirement, is satisfying the debris removal requirement. If any of this we say that is not satisfying and we need to change lubrication system, then we can refer the table which is given in this case. You see that if there is a too much speed, we provide a lesser lubricant or lesser viscosity oil, then there need to be some sort of circulation system of oil, or we can think about the gas lubrication. Now, you can think from any angle, any combination. Lesser viscosity oil, if existing lubrication system is fine, then we can say yes. Otherwise, we can think about the lubrication system which has a low flow rate, thicker oil will be fine, will high flow rate, low viscosity oil will prefer. And if not satisfying any of this, even after selecting this kind of low viscosity oil, it is not satisfying the requirement, then we need to think about the gaseous lubrication. However, if the operating temperature is very high, then we should choose a high VI. At the initial step, we are not choosing a high VI oil, which will be costly. Higher and higher VI will be more and more cost. And this oil need to have oil antioxidant additives. If you are purchasing oil from a market, then we need to tell vendor now we require antioxidant additives in that. or we can play with the design also. We can go ahead with the high flow rate of the viscosity or high flow rate of low viscosity oil. However, the operating temperature is only high, and we really do not require re-lubrication again because of the compactness or because of the additional system will reduce reliability. Then we can again still think about the solid lubricant as it is. Let operating temperature to be on higher side. Initially operating temperature maybe what we thought about the 70 degree, and we are not choosing we are choosing some liquid lubricant that is able to reduce to 70 degree, but it is going to cost me as more and more. That is why we can say now it is going to cost me more. I can think about the solid lubricant. Let operating temperature be 90 degree, maybe 100 degree. We will change the materials which are coming in a contact. We will go with by different materials. Sometimes we feel that too much debris because of the environment or because of the circumstances, then we need to use a recirculation system with the filtration, with the proper filtration. We require a longer life than or particularly longer life, we say that we do not want to think about replacing oil or oil system easily or quickly. Then we need to think about with the additives. Oil complete package additive will enhance the life. Finally comes too much load. In addition to any other earlier parameter, then we need to think about some sort of additives which can reduce the load or share the load, so that lesser load is coming on the surfaces. So, this is the last slide of this lecture. We can say that the final selection comes after fulfilling the second step. We say that if we are lubricating the surfaces and there are too many surfaces, not only the one pair which we are wearing. Take an example of IC engine. There are more than 20 tribo pairs in the IC engine. Then what will happen? We need to choose a lubricant for each tribo pair, which will not justify economic cost, reliability. We need to choose only one lubrication system, recirculation system, so that it can reduce the overall operating cost, inventory cost and initial cost. So, we choose a lubricant which satisfy or optimize overall performance. Here the one negative point we can go ahead, we can say that some places we require a low viscosity oil, but other places we require high viscosity oil. I will prefer with use of high viscosity oil compared to low viscosity oil to reduce the overall cost, initial as well as the running cost. Reason being, high viscosity oil is a self compensation. We discussed about this Strybeck curve earlier. We say that high viscosity, if the hydrodynamic action is happening and operating and one component operating temperature is coming over here, or the operating point is over here. In that situation, because of the self compensation, high viscosity will cause more friction, will reduce viscosity there. So, let viscosity plays with itself with this is a self healing process or a self adjusting process. So, with this I will try to close this lecture and this module, lubrication module. Now, it is time to deal with some mathematics to quantify what we have seen, that it will be moderate load, low load, high load, but we talk about some numbers. Our next module is based on that. We will be doing some sort of mathematical modeling, developing some equation and trying to use those equations. Thank you for your attention.